Hi everybody, this is Professor Iris Miano giving you day 22 lecture covering sections 7.1, 6.1, and 6.2. In 7.1 we will have a somewhat brief introduction to right triangle trigonometry. We're going to revisit this section a little bit later, getting deeper into the applications. We'll do one application today though, and then we'll follow that up with 2 sections worth of inverse trigonometric functions, finally introducing that notation of the exponent to the -1 power. Okay, so you may be familiar already with right triangle trigonometry somewhat. So I don't have much to say as far as introduction is concerned, other than to say that we will be dealing with right triangles, and generally the 2 legs are named lowercase a and lowercase b, and the hypotenuse is generally named c. The angle in question is often referred to as theta, and that's the angle that is fed into your trigonometric function, for which you are trying to find some sort of a ratio that gives the output value. As you can see in this yellow box here, with the sine, cosine, tangent is being redefined as opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent, or their corresponding lowercase letter labels. And then also their corresponding reciprocal functions, which are just indeed the reciprocal of those particular ratios already mentioned. So the way that it can be married to what we think about in unit circle is more or less illustrated in figure 1 part B right here, where we can see that the triangle fits into the location point on a circle, and if C happened to be taking on a value of 1, then we would have a unit circle. Okay, how these sides correspond to the theta that's mentioned is going to determine on its relative location. So if theta is in this angle position right here, then B, the length of B would be considered the opposite length to theta, whereas A is adjacent or touching angle theta, and so the word adjacent means next to, right? So we just want to use our common sense associated with the definition of the terms opposite and adjacent, and recognize what those location or what those distances are for the legs when the location of theta is known to us. And the hypotenuse is always just the longest side. C always opposite the right angle, and the right angle is represented by the little box in the corner. Probably things that didn't need to be said out loud, but there you go, just in case it's helpful. I wanted to just say all of that all in one go. There is a very important theorem that is presented here, and it's the complementary angle theorem. We're going to go through a couple of exercises in which we need this to come up with an equivalent value for a particular trigonometric function output. So for instance, and here's some good examples of this, if you want to, for a particular angle measurement, come up with, knowing the sign, right, of it, you can find an equivalent value for its co-function, cosine. You just have to plug inside of it the complementary angle. Complementary angles, just so that we're clear, are angles that sum to 90 degrees, or a right angle. So 30 and 60 are known as complementary angles because they sum to 90 degrees. Sine and cosine are co-functions. Tangent and cotangent are co-functions, and secant and cosecant are co-functions. Okay, so we'll keep those in mind when we find them to be relevant for exercises to come. Okay, and then the next item presented here is a really super generic right triangle, and the relationship between the side lengths lowercase a, lowercase b, lowercase c. It's the Pythagorean theorem, right? A squared plus b squared equals c squared. The sum of the squares of the legs equal the square of the hypotenuse for a right triangle. And also for a right triangle, capital A and capital B are representing the interior angle measurements for this figure 7 right triangle, and they always sum to 90 degrees. Why is that? Well, if you remember from your geometry days, the interior angles of a triangle have to sum to 180 degrees total. And if we're just dealing with right triangles, well, then that's 90 degrees taken care of right there. So how many degrees are left for the sum of the remaining two angles? Well, it has to be another 90 degrees, summing to, what's it called? 90 degrees. Yeah. Okay, cool. In this last figure, before we get into some exercises, I wanted to define an angle of elevation versus angle of depression. And it really has everything to do with how you are swinging either up or down from a horizontal line. That's the way I think of it. So I just make a horizontal line maybe with my arm if I wanted to do like a little kinesthetic element to this and to my learning of this, and say, okay, if I am going to, from a horizontal position, maybe have both of my, I know it's hard to visualize this because you're not seeing me, you're just hearing me, but put both of your arms over, both of your forearms over one another like you're a genie, okay? Like you're gonna, grant someone a wish, okay? And then swing one of your arms, like depending on if you put your left one over your right, like I'm doing right now, not that you can see, this is ridiculous, but go ahead and swing your left forearm up. That's illustrating an angle of elevation, okay? Now, keeping your arms in the same position, and I can demonstrate this in class if anybody's wondering what the heck I'm trying to say here. If you want to represent an angle of depression, you're going to take your right forearm, which for me is underneath my left one, and swing down. And then from that horizontal positioning, the swing down is representing an angle of depression. Okay. Cool. So, like I said earlier, we'll get deeper into more applications. I just have one at the end of this section to just have a little fun with, but those are the definitions to those terms. So when you see them in the describer of a word problem-y kind of thing from this section, you'll know how to create the illustration if one's not given to you. Okay, let's dive into some actual mathematical work here and figure out the exact value of the 6 trigonometric functions of the angle theta in each figure, starting with number 16. So notice we're given a right triangle in which the 2 leg lengths are given. The longer leg is length 2, and the shorter length is length square root of 3. So right away, I might want to just say, all right, my hypotenuse is some unknown length c. So I can use the Pythagorean theorem in order to calculate the value of c. So that'll be a squared plus b squared equals c squared, aka square root of 3 squared plus 2 squared equals c squared. Okay, so that'll yield a 3 here, 4 there, and therefore c is equal to the square root of 7. I know what the algebra heads are saying. Shouldn't it equal plus or minus the square root of 7? No, c is a distance, it's a length, so we're just going to take the principal square root, okay? Cool. Now that we know the value of c in a and b, or said another way, the value of c is also referred to as the hypotenuse, we can come up with the 6 trig functions. So the sine of theta is going to be opposite over hypotenuse, right? So katoa, did you guys ever learn it that way? So this is the way, one of the ways that I would think about it, opposite over hypotenuse. Well, what is the opposite length in regard to angle theta? Well, the opposite length will be the opposite side. Think of theta as like being maybe a light source, and where's it going to broadcast its light? Always on the opposite side, which in this case will be length of 2. So this one will be 2 over the square root of 7. But we do not like radicals in the denominator. So go ahead and rationalize this denominator, and you should have 2 root 7 over 7. Okay, next cosine theta. Cosine theta, ka, right? Adjacent over hypotenuse. So that'll be root 3 over root 7. Again, we've got that root 7 in the denominator. Rationalize that. We can talk about how to do that arithmetically in class if you want to, or we could just cut to the chase, and it'll be root 21 over 7 for the cosine of theta. And then tangent theta, toa, opposite over adjacent, that'll be 2 over root 3. Rationalizing that will be 2 root 3 over 3. And so I like to do sine, cosine, tangent first and then do the cosecant, secant, cotangent right next to it because they are just the corresponding reciprocals. And if I had in the original calculation a radical in the denominator, like I see with this 2 over root 7, I'm just going to straight up flip that one over and that'll give me my cosecant theta, which is root 7 over 2. That was quick and easy, right? So showing some of your work on here is kind of advantageous in this regard. Secant theta, therefore, will be root 21 over 3. Oh, that one's not as quick and easy. You'll flip it over. It'll be a root 7 over root 3. Rationalizing that denominator will yield root 27 over 3. And then we could just simply flip over this intermediate step for the cotangent theta and get root 3 over 2. Cool. And that's that. Just kind of box all that up. Let's do it one more time for number 18. Okay, so notice for number 18, we have a right triangle. Theta is positioned in this angle interior area, and we have one leg and the hypotenuse. So we're still going to use the Pythagorean theorem, but a little bit differently. Okay, so let's let maybe we'll let this side equal b. I'll just go ahead and label it. Oh, and I'll leave it that way. Sure. And so the Pythagorean theorem will be 2 squared plus b squared equals root 5 squared. Okay, and that'll yield 4 plus b squared equals 5. Therefore, b squared equals 1, which means b equals 1. Cool. So we can go ahead and just have it be like that. We have all of the side lengths, and so we can go ahead and figure out sine theta, cosine theta, and all the rest, tangent theta. So sine was so opposite over hypotenuse. That's 1 over root 5, which is root 5 over 5, rationalizing the denominator. Cosine is 2 over root 5. Rationalize yet again. 2 root 5 over 5 will be what you get there. And the tangent will be opposite over adjacent. So that'll be 1 over 2. Cool. Relatively quick and easy with this one, I think. Cosecant theta is going to be root 5 over 1, or just call it root 5. Secant is going to be root 5 over 2. And the cotangent is going to be 2 over 1, but just call it 2. All right, and that's it for that one. So remember, it's SOHCA, TOA, and then flip them over for cosecant, secant, and tangent. And there you have it. Okay, so for these next three here, we're going to go back and use this, complementary angle theorem. This stuff right here is the jam, okay? So remember, sine and cosine are cofunctions, tangent and cotangent are cofunctions, secant and cosecant are cofunctions. And you just need to put the complement of one angle to another when you switch from a particular function to its cofunction, and then you have an equivalent expression. Okay, so let's take this into account and find the value of each of these. So for 22, I want to recognize that the let me get a more reasonable writing utensil here. The cosine of 40 degrees, believe it or not, is actually equal to the sine of 50 degrees, using that cofunction relationship, right? Because we have cofunctions here, cofunctions. And then we have complementary angles. So I'll just kind of shorten it up there. So since they're equal to each other, we're going to be able to say that this is equal to 1. Let me go ahead and rewrite it. Hold on. So that means cosine 40 degrees, sine 50 degrees is actually equal to, I don't know, just pick one. Maybe I'll just make them both cosine 40 degrees, cosine 40 degrees. and that's equal to a big fat 1. Okay, cool. Let's keep this in mind for the next exercise. And we will want to, starting off looking at this cotangent of 40 degrees, I want to rewrite that in terms of cosine and sine, because I'm going to be able to then, I can see ahead that I'm going to be able to make a common denominator with the sine of 40 degrees that exists in this second term. So check this out. So I'm not even using the whole cofunction thing yet. I'm just going to redefine cotangent 40 degrees as cosine 40 degrees over sine 40 degrees. And that's minus sine 50 degrees over sine 40 degrees. Probably see where I'm going with this in the next step. Notice that the denominators match, so we can put cosine 40 degrees minus sine 50 degrees over a single sine 40 degrees. Okay, now we established earlier that cosine of 40 degrees is equal to the sine of 50 degrees. Didn't we do that? Yes, we happen to have established that right here in the previous problem. So we can, at this point, recognize that that's going to be equal to 0 in the numerator. It doesn't matter what the denominator's value is, that expression is going to have a value of 0. Again, we established earlier that cosine 40 degrees is equal to sine 50 degrees by virtue of their cofunctionality. So subtracting them from one another yields a 0. Okay, moving on. Last problem of this set. Okay, let's go ahead and right off the bat recognize that secant and cosecant are cofunctions, and we happen to have inside of each of them complementary angles. 35 degrees plus 55 degrees, guess what they sum to? 90 degrees indeed. We have the same thing happening with cotangent and tangent here with their degree measurements. So we can go ahead and say secant, oops, keep doing that, hold on. Secant of 35 degrees is equal to the cosecant 55 degrees. Furthermore, tangent 35 degrees is equal to cotangent 55 degrees. That being said, I have decided to modify these to be, well, I'm going to change the cosecant 55 degrees to a secant 35 degrees. So this first term is going to become secant squared 35 degrees. And then I'm going to subtract off. I'm going to change my cotangent 55 degrees to a tangent 35 degrees via this substitution here. And that'll yield a tangent squared 35 degrees. Cute. So at this point, I will redefine everything in terms of sines and cosines because I can see into the future with this and recognize I'm going to have a cosine squared 35 degrees common denominator. And let me show you how I get that. So secant is always 1 over the cosine, right? So that can be rewritten as 1 over cosine squared 35 degrees minus sine squared 35 degrees over cosine squared 35 degrees. Okay, put it all over 1 cosine squared 35 degrees. And what am I saying it goes over that? 1 over, oops, sorry, I miswrote. 1 minus sine squared 35 degrees. Okay. So 1 minus sine squared 35 degrees. We can use the Pythagorean identity to rewrite that as what? Guess what? Cosine squared 35 degrees. Indeed, anything over itself is just a big ol' 1. And there you have it. All this rigmarole in the beginning on number 28 just settled on down to simply a 1. Cool. All right. We have 2 more examples that I want to go over in this section, and then we'll get into that sine inverse business back in chapter 6. All right. let's take this next example in which we are given a generic right triangle of side lengths lowercase a, b, and c with interior angle measures capital A and B, and of course the right angle is identified by the box in the interior angle in the bottom right hand corner of the triangle. Cool. So we're going to use that figure, and we're going to use the given information that lowercase c's length is 10, A's angle measurement is 40 degrees, and so we need to find capital B's angle measurement and the lengths of lowercase a and b. Now for this one, you're actually going to need to use some sort of scientific calculator, but it's nothing that we can't handle, okay? I'll definitely describe the buttons you want to push for that. So right off the bat though, since we're dealing with a right triangle and I know one of the non-right angle measures, I can just take the complement of that and get the value of b. So therefore b equals 90 minus the 40 degrees for a, right? And so that'll be 50 degrees for b. Done deal. Okay, that was quick and easy. Now the harder part, okay? So I decided to go for the sine of 50 degrees to help me calculate the value of lowercase b, okay? And here's how I do it. The sine of the 50-degree angle, that's this capital B that I just calculated, right? The sine is opposite over hypotenuse, yeah? Okay. Well, the opposite side is lowercase b, and the hypotenuse is 10 that was given to me. So now I just need to find the sine of 50 degrees. So you're going to take your scientific calculator, and depending on the syntax, you'll either put in the 50 first and then press sine, or you'll press sine and then put the 50 in later. The one thing that you want to do before you get into the process of using your calculator, though, is to go into the settings or somehow figure out where the setting is according to the mode, because chances are your calculator is going to have a radian mode and a degree mode. You need to change it to degree mode if it's not already in that mode. So we could talk more about that with specific calculators in class, but for our purposes, let's just pretend that we are able to do this, whether we are or not. And so I'm going to press sine of 50 and press enter, and I will get 0.766044444. So I'll put B's approximate, that's, nope, hold the phone. That's just the sine of 50 is about 0.7660444, another 4 and a 3 1, and then it keeps going, but I don't, that's all of the values that my calculator will give me, and that's equal b over 10. So cool. We're going to multiply both sides by 10 to get an approximate value for b, and just round it to 2 decimal places is the convention. So that means b is approximately equal to 7.66. Okay, cool. Box that out, call it good. Lastly, we need to find the value of lowercase a. That's one of the leg lengths there. And so we can either do the sine of the 40-degree angle and label that a over 10, or we could do the cosine, the cosine of the 40-degree angle. Wait, did I say that earlier? I meant to say either you do the sine of the, the sine of the 40-degree angle or the cosine of the 50-degree angle. I'm going to choose to do the cosine of the 50-degree angle for no particular reason. Because then I'll do, the 50-degree angle is b, right? And the adjacent side is that a. Because, adjacent over hypotenuse, right? Which is 10. So the cosine of 50 degrees is 0.6427, I know, super boring, 6097, and that's equal to a over 10, multiply both sides by 10, so essentially move that decimal place over 2 spots, and then round to the nearest hundredth after that, and that'll give you an A value of approximately 6.43. And there you have it. So a little bit of calculator work, super minimal, and a basic scientific calculator can do this, okay? Just make sure you're in degree mode because our angle measures were in degrees. If our angle measures were in radians, which sometimes they will be when you need to use a calculator, mostly in the future, not necessarily this class, just make sure you change your mode to radians. Okay, last problem in this section. Let's go ahead and use some triangle trig to find the distance A to C across this pond in the illustrated figure. So, as you can tell, I super lifted this from the book. It is a cropped screenshot, as a lot of some of the formulas that I take are. So how are we going to move forward with finding the value of A to C distance? Well, we're going to assume that this is a right triangle right here. Okay, that is a fair assumption. It looks like one right there. So given that, we can determine that this other angle measure right here is 50 degrees. That looks very familiar. We've already been working with that combination of angle measures 40 and 50 for the complementary pair of acute angles besides the right angle. But we don't necessarily need that, do we? We have the adjacent side to the 40-degree angle, and we're trying to find the opposite side. Opposite is needed, adjacent is given. Does that make you think of any particular trigonometric function? Makes me think of the tangent. All right, so therefore, let's move take the tangent of 40 degrees, and let's give it the ratio of opposite. That's going to be our unknown length. Let's go ahead and give it some letter variable just to make the calculation easier. I'll call it x. So that'll be x. That's the opposite side, unknown length, and the adjacent side is 100. Cute and very fun to work with. Okay, do some button pushing. We're still in degree mode, right? And find the tangent of 40 degrees. So I get, from my calculator, 0.8390996312. That's equal, and dot, 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 equal x over 100, okay? So multiply both sides by 100, i.e. move the decimal place over 2 spots, and then round the remaining decimal to the nearest hundredth, and affix the appropriate units since there are some units in this particular problem. So that'll give you x is approximately 83.91 feet. And there you have it, folks. So that's a bit of triangle trig for you. We're going to revisit this section a little bit later on. When do we see it again? Next Tuesday. Okay, so a week, yeah, next Tuesday the 17th. All right, so just keep your feelings nice and warm in regard to those until then. Let's go ahead and finish up the rest of chapter 6, which is finally introducing inverse trigonometric function notation. So I just have various elements here from the section that I think are going to be helpful for us in getting through the exercises associated with these, and also introducing the new notation. So whenever we need to kind of more or less take apart the sine function, figure out what its inverse is, we will do so with this -1 exponent on the sine, which is just to say that if you have the inverse sine of x, well then that's going to become the output for the sine function, where the inverse sine output was a y, that will become the input. So just like with any inverse function that we've already encountered, the inputs become outputs and outputs become inputs. The domain and the range switch. Okay, and furthermore, it needs to be stated that both a function and its inverse also has to be a function. So that means that there are some pretty intense restrictions on a domain and the range for the inverse, because as you can see in figure 3 right here, concentrating first on the sine, which is in pink right here, This is just a very small piece of the sine wave. When you flip the inputs and the outputs, it's kind of like the sine wave is riding the y-axis instead of the x-axis, right? So as soon as you start to come down from the peak, well, what was synonymous to the peak in the sine function, right? The inverse come down from the peak is going to start to violate the vertical line test, making the inverse sine extension beyond x equals pi over 2 and negative pi over 2. Anything larger or smaller respectively than that is going to be violating the definition of a function, so it cannot be part of the inverse sine function. Okay, cool. So and yeah, the sine function itself has to also be restricted in regard to its corresponding inverse part. So as you can see in figure 4 right here, this blue part right here, that is the confines of the sine function that we take into account in illustrating the inverse, okay? And here's a little table of values within the domain and the range associated with the sine and sine inverse, okay? And then in this next yellow box right here, we get an idea of how to use how to composite the sine inside of itself. You can more or less have them cancel each other out, a sine and a sine inverse, right? And you'll just get simply the argument of x back out, so long as you stay within the domain of the, sorry, hold on. Oops, I'm zooming out here. As long as you stay within the appropriate interval. And so the appropriate interval, my bad, let's do that back again. When you're referring to x inside of the sine function, it's going to be from negative pi over 2 to pi over 2. And if you're talking about x inside of the inverse sine, you're going to have to limit that from negative 1 to 1, including those endpoints, okay? Cool. So if it doesn't make sense too much like why we would do that, I would refer back to figure 3 right here, where we have to limit the sine inverse so that we do not violate the definition of a function, okay? Because anything beyond these values right here for x, whether you're dealing with inputs or outputs, right? It's going to no longer be a function, and the inverse also has to be a function as well, okay? Now, we have similar things defined as I scroll down for the cosine function and its corresponding inverse. And look at this beautiful figure right here, laying the cosine function in pink alongside its cosine inverse function in blue. And of course, they're mirror reflections of one another of the y equals x axis, as all inverses graphically are. And again, we have to restrict the inputs and outputs in such a way that we do not violate the definition of a function. And so that's why your cosine and its inverse are limited to the inputs being between 1 and negative 1, and for the outputs, it's got to be between 0 and pi. So we'll keep this in mind when we do some of our exercises as well. And we're just taking, again, just this one chunk of the cosine function in consideration to calculating the inverse. That's all we can do. We can't take any more than that, because otherwise the inverse will violate the definition of the function. It'll fail the vertical line test, okay? Similarly, if we're going to compose a cosine function into its own inverse, they can cancel each other out, but only within these very specified intervals, depending on if you compose a cosine inside of the inverse or vice versa, okay? So we'll keep those things in mind as we go, because that'll sometimes eliminate some extraneous solutions. We can define this all in the same way for tangent as well. So take a look at tangent x, the original function here. It's that very cubic looking curve, and then here is the part of it, right? that can be defined as its inverse. So x can go, forever and ever and ever in both directions, but you're going to have a horizontal, right, asymptotes at negative pi over 2 and pi over 2, as you see here, okay? Right, that blue trajectory, the tangent inverse, is never going to cross those horizontal lines. Excuse me. Okay, cool. So we have these restrictions. Here's some, values just to remind you of inputs and outputs of just the basic tan function. And here are the ways that we are going to restrict function composition with the tangent, okay? So keeping all of these things in mind, let's get a little bit of practice in. Let's find the exact value of each expression for these three, and then we'll move on to a different type of a problem a little after that. Okay, so let's find the cosine of, just so I get my notes ready, cosine inverse of -1. So what I like to do with this is just set it equal to some dummy variable, okay? And so that's so I can rewrite it in such a way that I am thinking about it in the old way that we were thinking about it, right? So if cosine inverse of -1 equals x, then that means I can rewrite it as the cosine of x equals -1. So I've got to say to myself, okay, within the confines of the cosine x and its inverse function, what x's are going to give me an output of -1? Well, the only one that's going to fit is going to be x equals pi. And if it's helpful to refer back to unit circle, by all means do so. In fact, there's one exercise, and I think in this section, in which I'm going to need to refer to unit circle, and I provided it on the page for you because it gets to be a little bit wild how you have to jump around the unit circle, but we'll get to that in a second. All right. Let's do the same thing here for the tangent inverse of -1. I'm going to again set it equal to x. And then what's going to happen? Well, I can rewrite this as well. Tangent x equals -1. When does the tangent x equal -1? Well, that's going to happen at, within the range of values that are appropriate for x. That were mentioned earlier. That'll be x equals -pi over 4. All right, cool. So for this one, you can get a little bit tricky with it. Just to illustrate, you can have this -1 kind of be transferred over to the other side and then absorbed into the tangent function, and that's what makes it negative here, if that makes any sense. We could talk about that more in class if you like, but hopefully that's just kind of landing all on its own. You just let me know, okay? Now here, again, let's go ahead and set it equal to the dummy variable x, rewrite it as sine of x equals -√2 over 2. This is where looking at, what's it called? Unit circle is going to be kind of helpful. So when is the sine having an output of -√2 over 2? Well, it could be happening at either 7 pi over 4 or 5 pi over 4, right? But 7 pi over 4 and 5 pi over 4 are outside of that appropriate range for the sine. And so I'm going to have to recognize that 7 pi over 4 is actually within an appropriate range, and it's negative pi over 4 of a swing down from unit circle. So again, or you know what I could do? I'm actually going to do it this way and use the what's it called? The oddness of the function in order to get through this. I think that'll be a little bit better. Okay, so watch this, guys. Let's go ahead and multiply both sides by a -1, right? And then we'll get negative sine x equals positive now. this, root 2 over 2. Okay, and then I can use the oddness of it to say, all right, this is equal to the sine of negative x, root 2 over 2. So when do I have a root 2 over 2 for sine? Well, it could either be 3 pi over 4 or pi over 4, but which one is going to be within the appropriate range of values for x? It's going to be pi over 4, but it's got to be negative, okay? So under normal circumstances with no negative sign inside, I would say sine of x equaling root 2 over 2, x would equal pi over 4. But wait, it's negative. So slap on a negative sign there. And that's kind of more or less a similar thinking that I did over here for the tangent of x2. So hopefully that makes some good sense for us there. Okay. Now, we have some composite functions to deal with here, and they can get a little bit dicey, but don't worry. I've got a unit circle here that's going to help us, particularly with number 52. We've got to do some jumping around here. With number 40, though, we have an instance in which, since negative pi over 10, although that's not, a famous radian angle measure that we're used to working with, I know that pi over 10 is going to be less than pi over 2. So I know negative pi over 10 is going to be also within the confines of negative pi over 2. So it's within this range right here, right? Because it's the sign is between negative pi over 2 and pi over 2. If I'm not mistaken, doubly checking that right now. Indeed. Okay, good. So therefore, I can just go ahead and do this. Watch. Boop, boop. And this is my final answer. Negative pi over 10. Since this is x, or pi over 10, sorry, is between pi over 2 and negative pi over 2. Oh, and it's negative, sorry. There we go. Okay, but what happens when your input is larger or smaller, rather, or outside of the range of pi over 2 and negative pi over 2, right? What if it's not going to cut it? Well, then we need to do some fun jumping around here. So here's what I've done for this one. Where it's going. Okay, so first we're going to focus on this bit right here, just the sign of negative 3 pi over 4. So look at this on unit circle. Where's negative 3 pi over 4? Well, where's 3 pi over 4? 3 pi over 4 is right here, okay? So here is negative 3 pi over 4. So this is equivalent to negative 3 pi over 4. Just to be clear, as far as like the location is concerned, just this guy. And what is its sign? Well, its sign is going to be this negative root 2 over 2, right? Negative root 2 over 2. So I'm going to go ahead and just say that this is equivalent to, so sine inverse. I'm not even going to touch that just yet. Hold on. Sine of 5 pi over 4 is the same. Like 3 pi over 4 is this much swing, but in the downward, in the opposite direction, the clockwise direction, whereas positive radian swing would go in the counterclockwise position. Okay, cool. So that is the actual location traveling via negative rotation, and then this sine value is negative root 2 over 2, but we are not inside of the swing right here. Here's pi over 2, and here's negative pi over 2. So we need to be either in quadrants 1 or 4, right? You guys feel me on that? We need to be somewhere in here. And we're currently over here in quadrant 3, so we can't be there, but we can find a location that has the same sign value of negative root 2 over 2, and where's that? Well, this guy over here has the same sign of negative root 2 over 2, and its corresponding radian measure is, well, a positive 7 pi over 4, yeah? Okay, so that means that this has the same value as sine 7 pi over 4. But wait, when we're thinking about these things right here, we're supposed to be thinking about it as pi over 2, and this is supposed to be what? Negative pi over 2. So we're supposed to be thinking about all of these radian swings in quadrant 4 as their negative counterpart. So what would be the negative angle value that's equivalent to 7 pi over 4? So if I swing down this much, what would it be as a negative angle measurement? Well, look at the corresponding swing upwards. Well, if I swing that same amount as 7 pi over 4 downwards, it'd be the same as swinging upwards by pi over 4. So that means that this is equivalent to negative pi over 4. Right? And so then at this point I'd say to myself, oh, well, negative pi over 4, that's between positive pi over 2 and negative pi over 2. So at this point I am ready to slash these away, and I can have this equal to negative pi over 4. Whew! Yeah, trying to get to an output that's within the appropriate range that's mentioned before can sometimes be a little bit daunting, and I really highly recommend that you have a unit circle handy in order to make the jumps happen there. Okay, so hopefully that'll land it. I'm pleased to do another example of this type in class. Just let me know. But okay, in the interest of time, let's go ahead and move on to the next thing. What's the next thing? Okay, let's go ahead and find the inverse function of this sinusoidal function right here. Okay, so here we go. Remember how to find the inverse of a function, right? You're going to let f of x equal y, and then you're going to draw a line and say, all right, everything underneath here is now the inverse, and we're going to switch the x's and the y. So now it's going to be x equals 3 sine of 2y. And it's our job now to solve for y. Okay? So that'll be, first thing we'll want to do is divide both sides by 3. So that'll give us an x over 3 equals sine of 2y. Now why do we want to do that? Because then we want to take the inverse sine of both sides so that we can kind of cancel out the 2y on this side. Okay? So that'll be sine inverse of x over 3 is equal to the sine inverse of the sine of 2y. So we just kind of have to, assume that we're within the appropriate range here. We are. I mean, we don't know what this value is, but we assume that if we can do what we're doing, that we're in that appropriate range. So those will cancel, and then you'll have sine inverse of x over 3 is equal to 2y. So now it's just a matter of multiplying both sides by 1/2, and then we will have the inverse. So f inverse of x, therefore, equals 1/2 sine inverse of x over 3. Cool. So x over 3, huh? So it seems to me like we have, okay, so we were asked to find the range of f. So going back to the original function here, its range is going to be from -3 to +3. So, and including, right? So I'll just go ahead and put in an interval notation. So f's range is going to be this. So f's range is going to be f inverse's domain. Isn't that fun? No thought required. Because we just know how inverses work. Cool. And so then it just behooves us to figure out what the range of the inverse is. So what's going to be the F inverse range? Well, we have to think about this input right here, right? And so it being divided by 3, rather, or okay, sorry, we're cutting it in half, right? So that'll mean, because the original function's period changed from 2 pi, which is this parent sine function's period, to a pi, because, right, it was multiplied by 2. So that means that the period is now pi, but then we have to cut that. Just a moment, let me see. Where did I get that from? The range of F inverse is going to be, the F inverse, the sine inverse range is from pi over 2 to pi over 2, negative pi over 2 to pi over 2, right? But we got to cut it in half because we have this half coefficient out in front. Yeah, that's right. Okay, so that's going to make the range of the inverse function go from negative pi over 4 to pi over 4. All right, there we go, because that's going to be the domain of the original function, right? Cool. Got to take the pi over 2 to negative pi over 2 and cut it in half by virtue of having this 2 coefficient inside of the original sine function. Okay, cool. So I think we have all the elements there. Here's the inverse. Oops, I meant that. Let's get rid of that one. Box it up with our celestial marker. And here is the F inverse domain and range, and the F's, the original function's range. Cool. There it all is. All right. I think we only have 2 more of this section, and then we're going to expand our exercises to include the reciprocal functions as well for the trigonometric inverses. Okay, so here, let's go ahead and find these exact values, and we're going to want to, of course, solve for x. So let's start by dividing both sides by -4, which will give us tangent inverse, just a moment, of x equals negative pi over 4. So we're basically going to take the tangent of both sides, and this will work out well because, you know, we're inside of the, what's the word I'm looking for? The range that we want. That'll be the assumption here. And that'll be equal to tangent inverse. So we're essentially taking the tangent inverse of both sides. And they will indeed cancel out here, and we'll have x equals the tangent inverse of negative pi over 4, which if it was just the tangent inverse of pi over 4, it'd be a 1, but since it's negative, that means x will equal -1. Okay, let's do this one more time with a slightly more advanced problem. Here we're going to start off by combining like terms. So let's simultaneously add 3 pi to both sides. Add 3 pi. And then also subtract 5 sine inverse of x. Well, actually, we'll do that in another step. We're going to not do too much all at once. We'll have 5 sine inverse of x plus pi equals 2 sine inverse of x. So now we'll subtract 5 sine inverse of x from both sides, and it'll be pi equals 2 sine inverse of x minus 5 sine inverse of x. We're going to do a little bit of algebraic trickery here to say, on the right-hand side, we have a common factor of sine inverse of x, don't we? And the remaining factors are going to be 2 minus 5. See what I did there? So that'll give me a negative 3 times sine inverse of x. Okay, and I will divide both sides by negative 3, so a negative pi over 3 equals sine inverse of x. We'll take the sine of both sides. Watch this. Sine, and then sine of this. They'll cancel here. And we will have the sine of negative pi over 3. It's going to equal x. So sine of negative pi over 3 is equal to the negative sine of pi over 3, which will give us a negative root 3 over 2. All right. Whew. All right. So hopefully that's feeling good and landing real nice. Let's talk about it more in class if we need to, though. One last section. I don't have a lot of new stuff to cover. There's not a lot of visuals in this section, and I didn't create any new ones. So really, it's more or less a, what's it called? An algebraic construct here. Okay, so let's take into account these restricted bits here with this secant inverse, cosecant inverse, and cotangent inverse. So we're going to need the x to its absolute value to fall within a single unit measure. Y is going to range from 0 to pi, and it can't be pi over 2. Okay, so that's for the secant inverse of x. For the cosecant inverse of x, again, we have the same restriction on x, and y is going to range from negative pi over 2 to pi over 2, and it can't equal 0. The cotangent can be whatever it wants for x, but the y is going to be restricted from 0 to pi. Again, these restrictions are all about just taking a chunk of these original trigonometric functions so that they don't violate the definition of a function when you take their inverse. Okay, great. So let's just dive into some examples and we'll get you on your way to practicing on your own. Okay, so what I do here is I will, for this first one, because I have a composite function with different trigonometric functions here, so I cannot simply just cancel. That's not going to work, right? So I need to first take the argument and fiddle around with it. I'm going to use my dummy variable again and say that cosine inverse of 1/2, let's let that equal x. Okay, so you can let this equal x. Okay, well then let's just maybe solve for x right here and say, well, that means that the cosine of x equals 1/2. Okay, we'll work within the confines of, the inverse and say, well, what value of x am I allowed to have here? Well, x can be just a pi over 3. That's the only one that's going to work. Okay, now plug that into your sine function. What's the sine of pi over 3? Okay, well, that'll give you a root 3 over 2. Done deal. Okay, so if you take it into pieces like this, I think it's much easier to work with. Sorry, I got a little wild with my boxing there. I just want to box this part. That's my final answer. Okay, let's do this again, but with a cotangent and a tangent inverse. Again, just focus on this little bit, the argument of the cosine inverse, and the tangent inverse, and call it cosine 2 pi over 3 over sine 2 pi over 3. Okay, and luckily, or we could just go straight to the cotangent 2 pi over 3 if we know it. That'll be negative root 3 over 3. Because if we had the tangent of 2 pi over 3, that would be what? A negative root 3 if working within the confines of the whole inverse bit there. But then taking the tangent inverse of it, Whoops. Didn't have a bracket there to parenthesis. Okay, and using my dummy variable x, I'll get to say, okay, well, what tangent x gives me a negative root 3 over 3? Okay, well, knowing your unit circle stuff and the things beyond, you'll be able to conclude that x has to equal negative pi over 6. Again, and we're using the whole like oddness of this function to pull out the negative sign. Just say what's tangent x of root 3 over 3 and then negate it, okay? Just to be clear. Cool. All right, number 42. This one's a little bit simpler. Same instructions though, we're just gonna find the exact value of it. I'm gonna go straight to affixing my dummy variable here. Say it's equal to x, so that means that the secant of x has to equal negative 2. Cool, cool, cool. Well, that means the 1 over the cosine of x has to equal negative 2. Well, let's go ahead and flip both of them over. That means the cosine of x has to equal negative 1/2. When does the cosine of x equal negative 1/2? Again, within the appropriate range there. Well, that'll only be when x equals 2 pi over 3. 2 pi over 3. Yeah. So remember the cosine limitations are between 0 and pi. I know we've been working with sine a lot, which was negative pi over 2 to pi over 2, but this one's a little bit different, okay? So make sure you're making these adjustments as you're working with different trigonometric functions. Oh, yeah, I guess I'll box up my x's. It's just the x's used as my dummy variable. Okay, moving on. Let's get into some more complicated ones in which we are asked to write each trigonometric expression as an algebraic expression in U. So this is like a weird U substitution. It's really a theta substitution, the way that they outlined it in the textbook. And of course, I'm just going to go ahead and also use their guidance on this. So go ahead and let the argument of, in this case, your sine function, cosine inverse of U equal theta. Okay, very familiar input symbol for these trigonometric functions. And let's just go ahead and rewrite this original expression. So then sine of theta is what we're looking at, and we want to, so that'll just be a rewriting of this here, okay? But what do we get to glean from this? Well, if cosine inverse of U equals theta, then that means cosine of theta is equal to U. Okay, so let's manipulate this sine theta in such a way that we're going to have a cosine theta pop out of it. Okay, so think of your Pythagorean identities and just go nuts with this. So let's have a little bit of a sidebar in which we take the Pythagorean identity that we know pretty well that involves cosines and sines. This one is what I'm talking about. Okay, now take this and let's go ahead and solve for sine theta, okay? So we'll be able to replace this sine theta with what we have here. So solving for sine theta, we're going to subtract cosine squared theta from both sides. So that'll be sine squared theta equals 1 minus cosine squared theta. We've used this one a lot here, but let's go ahead and take the square root of both sides. And only the principal one, because, you know, we have to just work inside of the, you know, the positive stuff because we're in cosine. Okay, so that'll be sine theta, therefore, is equal to the square root of 1 minus cosine squared theta. Okay, so now let's go ahead and substitute this in. That'll equal no longer sine theta, it's the square root of 1 minus cosine squared theta. But wait, any cosine thetas? They are U, aren't they, right? So let's go ahead and take this cosine squared theta and replace it with a U, and then we've done exactly the thing that they asked us to do, to rewrite the expression in terms of U right here. Okay, so this will therefore equal the square root of 1 minus U squared. And that's what they were after. Let's do this again, but for a different example. Let's do this actually 2 more times, and then we're going to be done for the video. Yep, that'll be all that I have for you here. Okay, so again, let's take the argument and set it equal to theta. That's always your first move, okay? So then you get to use the cosine equivalent, in this case, for this cosine inverse expression, and say, well, that means cosine of theta must equal u. So we're going to use this to eventually manipulate tangent theta in such a way that we'll be able to write it in terms of u's, okay? So what did I do for this one? Let's see. Here's number 16. Yep, so I used the Pythagorean identity involving tangent and secant, right? Tangent squareds and secant squared. So you can do a similar sidebar in order to redefine the tangent theta as something very familiar to the previous problem, the square root of secant squared theta minus 1, right? But wait, the secant squared theta is 1 over cosine squared theta, yeah? Cosine theta, it happens to be squared here, that's u. So now we can finally write it in its final form of 1 over u squared minus 1, all inside of the radical. Alrighty, great. One more time. Let's where's my last page? Here we go. And this one's so easy it's hard. Watch this. Okay, so take again the argument secant inverse of u, set it equal to theta, right? Well, if that's the case, then that means the secant of theta equals u. Furthermore, this means 1 over the cosine theta equals u. All right? And therefore, also, cosine theta equals 1 over u. Now, what do you get when you replace the secant inverse u by a theta? Well, you get a cosine of theta. But what did I just define cosine theta as? 1 over u. Bing, bang, boom. Donezo. All right, so let me know on Thursday what we want to dive a little deeper in, more examples, more demonstrations. I'm delighted to do it. Let's tell me what's not landing here and I will make it all better. Okay, guys, see you Thursday.